The topic of this talk is duct tails, trimming the tail latency of packet processing systems. The motivation for this talk is the 5G ultra-reliable low-latency communication standard, or short URLLC. The URLLC was defined by ITU, meaning that ultra-reliable means 99.999% of all packets must successfully arrive at the destination, and this all should happen with a low latency, which means that we have a latency budget of 1 millisecond. This means we have a one-way delay end-to-end in the radio access network that is below or equal to 1 millisecond. So to test if this is actually possible to achieve on typical software packet processing systems, we took one of our servers using Linux and KVM as a hypervisor. There we ran a network function, in our case a SNOT3 intrusion prevention system, but we configured it without any filtering operations happening, so we basically just configured SNOT3 in this case as a forwarder, and then we measured the latency that could be achieved between the ingress and the egress interface of this SNOT forwarder. What we got was the following table. So here we can see the percentiles that we actually measured for the basic SNOT3 forwarder. So up to the 99.9th percentile, everything is fine. So we stay well below our 1 millisecond budget. However, if we consider also more rare events, this means that we actually violate our latency goal by quite a significant amount. So we have a maximum latency in the 99.999 percentile of 2.5 milliseconds. So this is more than twice what we actually want to achieve. So we took also a closer look into the latency that we measured. This is displayed on the following graph. So here we have the actual latency over a period of 30 seconds. Then we can see that some of these packets, or many of these packets, create some spikes in latency that is then even above 2.5 milliseconds. And what we can also see is that there's no clear regular pattern visible. So we don't see any common reason, at least from this perspective, that could cause something like that. So this was basically the reason why we started our investigation. So first of all, we want to investigate what kind of techniques or mechanisms cause these irregular measurements or these irregular latency events. So therefore we had a look at the typical Linux system that we just tested. So the first reason that we found for these irregular spikes was the interrupt-based I/O of Linux. So this is also called NAPI. And this means that for each packet that we receive, a latency or a interrupt is triggered that interrupts the currently running process. So if we host a packet processing application and a new packet arrives, this packet processing application may be interrupted, the newly arrived packet handled, before we go back to our original application and process the rest of the packets further. So this means that we have some inconsistencies or irregular events interrupting our application. We also have certain CPU features that might cause these interrupts or these latency events. This means that we, for instance, have dynamic scheduling of processes onto CPU cores. That means if we move processes between different CPU cores, this always causes some overhead, which then results in the latency that we measured. We also could have virtual cores enabled, also called simultaneous multi-threading or hyper-threading. This means that two virtual cores are hosted on a common physical core, and this might lead to resource contention if two different processes running on the two virtual cores at the same time request the same resources from the physical CPU core. What also can happen is that we put our CPU cores into a sleep state, and changing back to a running application means that we have to wake up this CPU core, and this involves additional latency. We also have some kind of dynamic cache allocation for a shared cache between all of these cores. So this can lead to resource contention of certain portions of the cache and thereby also cause additional latency. And finally, we also identified the in-output operations into and out of VMs to be highly costly. So these are all reasons why our latency events look like what we just saw. So how we can fix that is listed in this table or on this listing. We have switched now to a polling-based I/O. This means that we use a specialized framework, in our case DPDK, that just relies on polling, and this makes the entire packet processing more predictable, because now the application decides when to receive and send packets exactly. We also enabled and disabled certain CPU features, one of them being that we now statically allocate CPU cores for processors. This means that we pin specific applications that we want to run with low latency to a specific CPU core, so we don't change the CPU cores all the time. We also disable simultaneous multi-threading or hyper-threading entirely. This means no virtual cores fighting for the same resources. We also disable all of the energy saving mechanisms of our CPU. This means, of course, that we have a higher energy consumption, but at the same time our performance gets more reliable. And in the end, we also configured our shared cache to only use certain cores. So we fixed the number of, or the amount of cache that a certain core can use. This can be done using the Intel Cache Allocation tool, or short IntelCAT. And finally, we also enabled hardware acceleration mechanisms on our VM. This means that our virtual network or our physical network card can now be split into several virtual functions via a function called single root I/O virtualization. And this enables us to have an exclusive access to these virtual functions from our VM that should accelerate our in-output operation. So how does now a system look like if you put all of these things together? So here we have a quad-core CPU, and what we can see is that the host system, or the operating system of the host, is just bound to a single core, in our case core 0, and all the other cores are not bothered by the operating system any longer. This allows us to host a VM on cores 1 and 2, and there we do basically the same thing. We bind the operating system to core 1, and this leaves pcore 2 free from any impact of the VM operating system and the host operating system. So additionally, we also activate the virtual function on the network card and bind it exclusively to our pcore 2. And this now allows us to have a uninterrupted path between the network card and our pcore 2 hosting the application that we want to run. We also activated a special feature called no hertz, or no hertz full. This allows us, this is a feature of the Linux kernel that allows us to disable all interrupts on pcore 2, or at least a very high amount of them. So when we now want to measure, we did it in the following setup. So we created a very basic setup with the two servers on top. Then we have a load generator on the left that generates and receives packet back from the device under test. And the device under test is a simple server that is just configured to forward packets between its two interfaces. For the network cards, we only use Intel X5510. 552 NICs that support 10 gigabit Ethernet, and all of these computers use the CMD processor that is a quad-core processor with 2.2 gigahertz. Our setup also involves a third machine called timestamper. So this is here to record all packets exchanged between the load generator and the device under test. One thing special about the timestamper is that this timestamper actually can timestamp every packet that it sees in hardware. So this allows us a very precise and accurate timestamping of all the packets that we see. We connect these 3 computers using optical tabs. So the timestamper actually can really monitor everything passively via these optical tabs, so we don't have any switch that might influence our latency in between. So this is entirely passive and should not influence latency. We also have measured with UDP traffic. This means we don't have any impact of the TCP protocol on the latency that we measure. We additionally use destination port 53. So if we want to measure something using our SNORD3 rule set, we can now match against the DNS rules, and we use constant bitrate traffic. So first I want to explain why we rely on hardware timestamping. So this is actually 2 reasons, and these are the accuracy and the precision that we want to achieve. So accuracy and precision are 2 quality measures when it comes to the latency that are explained in the figure above. So on the right, or on the left, we have this real distribution that the actual system has, and then we have our measured distribution on the right side. A very high accuracy in our case means now that we have a possibly low distance between these 2 distributions. So the accuracy, very informally explained, is the closeness of the real latency and the measured latency. And at the same time, we also want to have a measurement distribution that is very close to each other. So this means that a high precision explains that the measured distribution is quite small and has no statistical outliers from time to time, for instance. So why should we now measure in hardware? So the first reason is that if we measure the timestamps entirely in software, this would mean that we had to receive the packets, deserialize the packets, send it via PCI Express over to the CPU, and only at the CPU we could then create our timestamp in software. This is of course some time between the actual reception of the packet and the timestamping process, and to keep that short, we now move the timestamping process to our network card, and this allows a higher latency, a higher accuracy of the latency in this case. The same also holds for the high precision that we want to achieve. So if we measure in our operating system, the operating system can be subject to some kind of OS interrupt, and this would of course then impact our latency measurements if we have a interrupt that would lead to statistical outliers from time to time. So hardware timestamping therefore is the best solution to our problem, which allows a high accuracy and high precision at the same time. So after we have cleared up that, we can now go over to our actual measurements. So the measurements that we performed are based on 3 different kinds of forwarders. This means that we have first of all, we have a baseline measurement. Therefore, we use the DBDK layer 2 forwarder. This is just a minimal program that we can actually determine how much the overhead for the actual input and output operation based on DBDK is. Then we create this slightly more complex forwarder by introducing SNORD on top of DBDK. This means that we now use SNORD, or DBDK again receives the packet, hands it over to SNORD, SNORD forwards the packet and then sends it out again via DBDK. And to create a more realistic application, in the third step we then also activate in this SNORD forwarder the community rule set, and this then allows us to determine how costly the actual rule application is. The whole or all 3 forwarders are then also investigated in 2 different deployments. One of the deployments actually runs on bare metal hardware and one of them in a VM. So over to the real results. This can be seen in this graph. So here we have actually the latency distribution in percentiles. on the x-axis and the latency displayed on the y-axis. We also measured for different throughput values. So we measured here for 10,000 packets, 60,000 and 120,000 packets per second. And we measured, as I already said, on hardware and on the virtual machines. And what we can see is that the performance or the latency performance is quite stable up to roughly 99.9, up to the 99.9 percentile. There it raises a little bit up to 4 microseconds. So this is quite a low latency. So we're totally in our 1 millisecond budget. What can be also deducted from this measurement is that there's actually a very little cost between the hardware and the VM. So this means that the costs of virtualization are quite low. What this also shows is that the higher the rates, the later the latency increases. So for a rate of 10,000, we have this latency increase observed at a 99.9 percentile. For the other throughput rates, we see it later up to the 99.999 percentile for the 120,000 packets per second. So this result suggests that the source of the higher delay is actually independent of the packet rate. So we had a closer investigation of this measurement. So therefore we again plotted the measurement over the 30-second measurement period. What you can see here now is the worst case latency that we measured over the 30-second period. And here we can see that we have a bar at roughly 3.3 microseconds. This means that most of the events are in this horizontal bar. However, we also have this dot or these dots on top with a very regular pattern in this case. So between these single or few dots on top, we always see a 1 millisecond distance in between them. And there are just a few every second, basically. So this indicates that there is a common cause that causes these 1 second latency events. However, we did not find a root cause yet. So we investigated the Linux system and actually investigated if some interrupts are happening, but Linux does not report any interrupts in this case. So proc interrupts was totally empty. And currently we have only very rough ideas what could happen. So one of the ideas is that DBDK might actually have this 1 second process that is triggered every second, or that the PCI Express has some kind of clock behavior, but we're not sure for now. Then we want to also investigate what the snort forwarder can actually do. And there we can see that, back again to the HDR latency plot, that we have now a slightly higher latency, roughly 20 microseconds in the typical use case. However, we can see that if we overload our system, this happens between 80 and 90,000 packets for this configuration, is that the latency is significantly higher in the millisecond area. So 3 milliseconds for the VM, 30 milliseconds for the hardware. The reason why the VM is lower in this case is that the amount of buffer that is available to the virtual function is distributed across several virtual functions, therefore the latency is lower in this case. However, we violate our 1 millisecond goal all the time, so this is actually not a viable solution to overload our system. So we should avoid overload at all costs. We also now can activate our rule set that leads to the following results. There we can see that, again, the latency significantly rises if we overload the system, but now the overload actually happens at a lower point. So here we actually overload our system between 60 and 70,000 packets for the hardware use case and 60 and 80,000 packets per second for the VM. So This demonstrates that the start of the overload actually depends on the complexity of our processing task. Then we also investigated how the real-time patches for the Linux kernel that should make the entire performance more predictable behave compared to our no-hertz kernel. And all the other parameters were basically left the same, so we also disabled all the energy settings, the core isolation, and so on. The results are plotted here. So here we see the relative difference between what we actually measured. So if you follow this rough shape of the plots, you can see that for the lower percentiles, this is up to roughly the 90th percentile, we cannot see any difference. So we are at a relative difference of 100%, meaning that we actually see basically the same latency for the real-time system and the no-hertz system. However, if we look at the higher percentiles, we can then see that the latency is quite significantly lower for our no-hertz kernel. So in the most extreme case, we see a latency improvement of up to 400%. However, this thing only is valid for the non-overload scenario. This means in the no-overload scenario, we don't see any latency improvement, regardless real-time kernel or a no-hertz kernel. We then actually had one very special event called transition look-aside buffer shoot-down. So first of all, what is the transition look-aside buffer? This is basically a cache implemented on modern CPUs that caches the virtual to physical memory address translations. Certain operations may now invalidate this cache, and in case this invalidation is necessary, a TLB shootdown is created that is realized as an interrupt that causes latency. So for our use case, we actually had a look at a certain website, and this uncovered that certain operations, for instance, the unmapping of memory or the setting of protection flags, causes these TLB shootdowns. In our use case, it was possible to actually prevent them because the SNOT 3 forwarding program actually performed the unmapping operations only in the beginning of the application start, basically. So we just started now our application, and then we let this TLB shootdown happen. And after that, we basically got the nice latency performance that we wanted to achieve. This can be also seen in this graph. There we can see that only at the beginning we have these TLB shootdowns that cause these high latencies, and after that we basically get our nice performance again. So just as a remark, we our entire measurement artifacts are publicly available. So here you can see that we realize the experiment scripts, the measurement data, and the plotting scripts as well. The tools and the experiment scripts are explained on a nice website that you can see on the right. And the entire measurement data that we used to create our graphs in the paper and the presentation is available in a GitHub repository at this link. Okay, so let's come to the conclusion. What we have shown in the last few minutes is that the low latency packet processing entirely in software is in fact possible. However, we also demonstrated that the device under test must not be overloaded. So in the overload use case, we get very poor latency performance. So we should avoid this point of overload at all costs. We also have shown that the no-hertz option can significantly reduce tail latency, even compared to a real-time Linux that already has an improved predictability and latency performance. We also have shown that we still, despite the no-hertz option, have some kind of latency pattern, but we could not determine the root source for now. And we also demonstrated that despite we deactivated most of the interrupts, there still might happen, some interrupts on certain systems, called TLB shootdowns. However, we also shown some methods to actually circumvent these shootdowns, at least for our application. So thank you for listening. I'm now open to your questions.